Hello, my name is Marco Proitali and I'm going to present part of the work carried out during my PhD, which was applied specifically to high deformation barriers for rockfall, but I think can be applied to a lot of different issues related to georesilience and mitigation. Specifically, in our case, what we wanted to obtain was the deformation in time of a rockfall barrier in order to compare it with our numerical results. And unfortunately, there is basically no data available in literature because from physical tests only very little data is extracted, which is typically big deformation breaking time. So this is what we wanted to obtain. So moving forward, what we try to do is find how to obtain a continuous deformation profile. And from what you could see in the literature, there is a lot of technologies, more and more advanced technologies have been used to obtain profiles or evolution, 3D deformation evolution in time. The issue is all these techniques, for example, PAV, DSE in 3D, or 4D photogrammetry, are based on sub-pixel estimation, which means for a test characterized by dynamic deformation and quite a nice speed, you need a very expensive hardware to, well, get any valuable data. Additionally, for redundancy purposes, you might want to use other measurement techniques, for example, inertial measurement units. However, for what we encountered looking at the literature, there is basically no commercially pre-packaged solution that can record with the rates and precision required. And the people that encountered this problem before had to build their own systems, typically using microelectronics and microsoldering, for which we didn't have any background or expertise. So what we did here, in order to obtain a continuous deformation profile, rather than using standard pixel-pixel correlation techniques, we decided to track a limited number of targets placed on the object. For example, here you have a cloth which you use to verify this approach, but it can be done on the field using the barrier, it can be done on a moving object such as debris flow. The main advantage of using color targets, which we separated from the background using HSV-U based thresholding, is that we can, instead of separating everything based on the intensity, which can change a lot in the field due to natural lighting, it's much easier to separate avoiding the colors that you can find in the field, for example red or purples, which are not typically occurring. Okay, after the target has been binarized, the Mancre's algorithm is used to assign a set of tracks in order to establish relationships between points highlighted in each different frame and to obtain a continuous deformation instead of having random points without any specific spatial correlation between each other. And additionally, the Kalman filter is used to predict where a specific target is moving in space, as you can see here, so that when, for example, if you have an obstruction or large deformation of a cloth that prevents the object from being seen, the Kalman filter predicts that the object is moving in this direction from the previous steps, and is used to find then the object again in the next frame where the object becomes visible. From the 2D pixel space position of the target, of each individual target, it's possible to reconstruct the 3D position of each target using standard stereo camera techniques, in which the position and the calibration of each camera can be obtained automatically by any free packages such as OpenCV or MATLAB, and using a checkboard calibration. Then the position in 3D and the displacement in 3D of each point can be obtained very easily. Then in regards to the inertial measurement unit, since we wanted to have an additional source of data for when a specific target was no longer visible in the cameras, we tried using inertial measurement units. In this case, looking in the literature, we couldn't find any available solution, but using microelectronics and breakout boards, we found out that it's very easy to connect using jumper cables or produce a very inexpensive sensor. I think this whole system costed like 20 pounds in total, and we just separated the object itself, or the microcontroller and the recording system from the sensor using an Ethernet cable, and connected everything to a power bank, so it would be very easy to bring on the field without having to worry about, well, converting using inverters or anything of the sort. The data is recorded, and then simply using a Butterworth filter, it's possible to carry out or clean the data and carry out double integration in order to obtain the displacement of the point in space using inertial measurement units. Then the system was verified under both quasi-static and dynamic conditions. For the quasi-static condition, a cloth was displaced using a box, and the entire deformation was recorded using our accelerometer and cameras, as well as a 3D scan using a LiDAR, which was then used as ground truth for comparison. So on the left you can see the full deformation of the cloth at maximum deformation, captured using LiDAR, and the slice of this deformation, which shows the displacement. In red you can see the target and the inertial measurement unit, which recorded data that was not usable per se to obtain the displacement, because it was a very long test, and therefore the noise tends to sum and produce unusable data. But you can see here the change in the gravity vector, which confirmed that the entity of the displacement measured with the inertial sensor were the same as with image analysis and with LiDAR. In the same test, image analysis has been used to find the displacement of each target, and as you can see in the manuscript itself and in the attached material, there is very little discrepancy between the ground truth obtained using the LiDAR and the data obtained using image analysis. The dynamic test was carried out by impacting the cloth with a tennis ball, and instead of recording the displacement for the entire surface, all we did was record the displacement in the center using a continuous LiDAR scan. So this is the setup. The rest of the setup was the same as for the quasi-static test. This results in a 2D profile in the center of the cloth that changes with time, and considering that the target is placed in the center of the cloth, as highlighted with the dashed black line, it's possible to obtain the time displacement orthogonal to the initial cloth position of the target, which can then be used to compare with the image analysis and with the inertial measurement unit. Then the data acquired by the inertial measurement unit, which is acceleration, is corrected considering sensor orientation, which is obtained by gyroscopes, as you can see here, by removing the ambient noise through a low-pass filtering using Butterworth filtering, as you can see here, and removing sensor noise or constant noise or drift by removing linear trends. This corresponds finally to the continuous lines, which can then be compared to image analysis and LiDAR, which you can see here that tends to overlap quite well with the available data. We consider that might be some discrepancy due to the fact that each system is monitoring something else, and the IMU data can move non-axially outside of the position of the laser scanner, but other than that the data seems to be very close together or very similar to each other. And in conclusions, we then use all this system to carry out impact tests, and we simply used cell phones and very cheap cameras to obtain all this deformation using color-based thresholding and open source codes. And at the same time, the microelectronic sensor were used simply with breakout ports without having any specific skill required. And all the code that we developed for this is available in the attached material, and there is more information on the paper as well. Thank you for your attention.